2019 paper 1. Questions about different pH values. Pure water, pH is 6.67. Okay, fine. So the pH has dropped, probably because you've increased the temperature and broken some of the bonds, so the water is dissociated into H plus and OH minus ions, so you've got a larger concentration of H plus. The student thought the water was acidic. No, just because you've got more H plus in the mix doesn't mean that it's acidic. It's neutral, because for pure water, H plus concentration equals OH minus concentration. Nothing to do with pH. pH is minus log to the base 10 of H plus concentration. pH is giving you 6.67. What can we do with that? We can work out H plus concentration by inverse logging minus 6.67. 2.138 times 10 to the minus 7. Now, what's it asking me for? It's asking for Kw. Kw equals H plus multiplied by OH minus concentration. The H plus and the OH minus have come from the dissociation of water, so as the water molecules are split, it's making one H plus and one OH minus. They must be equal, so I can turn H plus concentration, OH minus concentration into H plus concentration squared. Kw equals 2.138 times 10 to the minus 7 squared, 4.57 times 10 to the minus 14. I've got a curve here. It looks as if I'm adding sodium hydroxide to an acid. The acid starts off at pH 3, so it's weakish, and it's propanoic acid, and it's ending up as pH 12. Sodium hydroxide, I expect to be a bit higher than that as a strong acid, a strong base that fully dissociates in water, but it's ended up at pH 12. Okay, it looks as if we're adding sodium hydroxide from the burette in small amounts and measuring the pH with a pH meter and plotting a curve. So, what can I do with this? Use the figure to determine Ka. Well, what I need to know is this. At half equivalence point, so equivalence is where the acid and the base have reacted, so I'm going along from pH 7, where the two have reacted together, or the middle of the point that it's going up rapidly, and I'm reading down from there, and it's turning out to be 19.5 centimetre cubed of sodium hydroxide is added to get to equivalence point. If I halve that, 19.5 divided by 2 is 9.75. Now read up from 9.75 and I find the pH at that point. Reading up from 9.75, the pH is about 4.9. There's something you've got to learn. The pH at half equivalence point, where you've added half of the sodium hydroxide that you need to add to get the two to react and reach equivalence, equals pKa. Now pKa is minus log to the base 10 of Ka, so 4.9 equals minus log to the base 10 of Ka, minus 4.9 is log to the base 10 of Ka, inverse log minus 4.9, 1.26 times 10 to the minus 5. So just to go over that again, you find the point that it's shooting up rapidly. You find the middle of that section. It's usually around about pH 7, it's a bit higher, it's around about pH 9, but there's about 19.5 centimetre cubed added to get to halfway up that point where it's shooting up rapidly, the equivalence point. And over half 19.5 divided by 2, 9.75, I find the pH of 9.75 centimetre cubed of sodium hydroxide has been added. At that point, pH equals pKa, or minus log to the base 10 of Ka. And I can work out then Ka by inverse logging minus 4.9. Suggest which indicator is the most appropriate for the reaction. Well, I'm looking at where it's going up rapidly. It's going up rapidly between pH 7 and pH 11. So I'm looking for an indicator that works between pH 7 and pH 11. The range of the indicator has got to fit right between pH 7 and pH 11. So it's got to start higher than pH 7 and end up below pH 11. So the answer is cresol phenol phthalate. Student prepared a buffer solution, 0.0136 moles of a salt Kx to 100 centimetre cubed with 0.5 mole per decimetre cubed of a weak acid. So first of all, I've got a volume and concentration of a weak acid. Let's work out number of moles. Moles is the concentration multiplied by the volume in decimetre cubed, 0.1 multiplied by 0.1 is the volume in decimeter cube, multiplied by 0.5, which is the concentration. I've worked out the number of moles of HX is 0.05. Now, HX, this fictitious acid, will make H plus X minus, so I've written an equilibrium expression, H plus concentration multiplied by X minus concentration divided by HX concentration. The buffers I cancel a brackets top and bottom and leave H plus concentration alone. So that's moles of X minus divided by moles of HX. How do I find out the amounts of those? Well, I've got the Ka, so I've plugged that in, 1.41 times 10 to the minus 6. How do I find out moles of X minus? Moles of X minus is the amount of the salt. So that is 0.0136, because it's told me that in the question. If you're given an acid and a base adding together to make a salt, it's the number of moles of the base at the beginning. But in this question you aren't, but it's either the number of moles of salt that's made or the number of moles of the base, like sodium hydroxide that's added at the beginning, 0.0136. And it's divided by the number of moles of acid, either that you've got in the solution or you've got in excess. Now, I've not added a base and an acid together, so it's not neutralising each other, so I'm not ending up with any HS in excess, it's just whatever's in there to start with. And the number of moles of HX we've worked out is 0.05. Now that would be fine, and I could work out H plus and I could work out pH if I wanted to. However, the question is more difficult than that. Calculate the pH of the buffer when I add potassium hydroxide. If you watch one of the earlier videos, if I add potassium hydroxide, which is a base, I add that number of moles to the top and I take it off the bottom. If it said add acid, I add acid to the bottom and take it off the top. So for potassium hydroxide, I add that number of moles, 0.0003, 3 times 10 to the minus 4, to the top, and I subtract it from the bottom. Once I've done that, I can recalculate, I can find H plus, and I can find pH. Strange little question this. A buffer solution is a constant pH even when diluted. Use a mathematical expression to explain this for 1 mark. In the examiner's report, very few people got this. An odd question. So if Ka equals H plus concentration X minus concentration divided by HX, a buffer has a constant pH. So H plus concentration is staying pretty much the same, and the Ka will stay pretty much the same for a buffer solution. So my equilibrium constant stays the same. It would stay the same unless I change temperature. So Ka is staying the same because I've not changed temperature. H plus concentration is staying pretty much the same because pH is staying pretty much the same. That's what a buffer solution does. So I've replaced Ka with a constant, I've replaced H plus with a constant, which means that I've got constants in there not changing, and Hx divided by X minus must remain constant. A strange kind of question, that.